Alright, you are nearly fully trained measurement invariance ninjas, right? So if you look at all that code, that is like awesome heavy lifting. As you remember, we ran we specified our model, and then we had to run all these different tests separately, right? So we would run our configurable invariance test by running our standard CFI command and adding a group statement, right? So where we would run and test the parameters separately by country, so basically by sample. And then if we wanted to constrain, let's say, for example, the loadings to test for metric invariance or metric equivalence, then we had to basically add that manually. Group equals quotation marks loadings, and then we would need to compare via the ANOVA command the difference in chi-square, and we could ask for the fit measures separately for the configurable and the metric model, and then we have to compute basically by hand the difference in fit between these two models. And the same for the full score or scalar test, where we now constrain both the loadings and the intercepts to be equal across all the different groups in our data set. And then again, we need to run the ANOVA to get the difference in chi-square, and then the fit measures to get an easy overview of the different fit indices. There's actually a very cool little tool available via SemTools, one of the packages that we loaded earlier, that gives us an omnibus test that runs all these different comparisons already in one single go. And we will see in a second how that works, and also why there's a little problem with that, but let's go through that. The command is actually called measurement invariance here, and we need to specify our model first. Our model in our case is called model 1. We need to specify what is the data. Data, in our case it's data example, and we need to specify the grouping. In our case it is country. Remember, put it in quotation marks. Now if we run it, it takes a second because it's kind of heavy stats going, and we will get our output. And as you can see, first of all, this is giving us the command again, and then it runs essentially 4 different models: the configurable, a loadings, an intercept model, and also it tests whether the means are actually, the latent means are equal or not. And first it gives us the chi-square difference test. As you could probably imagine, and as you probably will remember from when we did it manually, it's pretty bad news from the chi-square test perspective, because both the loadings and the intercepts are significantly different as we go from more lenient or less restrictive models like the configurable model to metric invariance model. The chi-square difference is 82, with a difference in 30 degrees of freedom, and that's highly significant. If we go from the metric to the full score scalar invariance model, the difference in chi-square is actually 300, and again it's highly significant, and so on. So it's not good news. If we look at the CFIs and the RMSEAs and the difference between them, so as you can see here, the difference for CFI and the difference for RMSEA is actually pretty good if we go from the configurable to the metric invariance model, where we constrain the loadings to be equal. So that value is actually below the crucial threshold of 0.01, and the same for the RMSEA. If we go from the restricted loadings to also restricted or constrained intercepts. As you can see now, at least for the CFI, we are above our magic value that we don't want to cross, so 0.01. So this little command is making life so much easier. The reason why I alluded to, potential problems is that little red warning down here. We still have it, but it won't be available in the near future. So unfortunately, even though this command is so good, it won't be around for much longer. So what we decided to do with the cc_psych package, we kind of grabbed something equivalent and included it in the cc_psych package. So if we go and call it through the cc_psych package, we called our command equival for equivalence, and we also have to state essentially what model we want to run. So we can just say what model. We don't need to say specifically the model, but we have to say what data we want to call it on. So data example. We have to specify the grouping. It's still country, and then there are some kind of arbitrary extra little things that we needed to also set. We have to say specifically how the latent variable was identified, and in our case we if you remember, we set the model identification via standardizing the latent variable to 1, right? So we have to say that it is true that the the latent variables are set to be 1 to be equal across groups for identification purposes. And then there's a odd little command which we just have to state here: orthogonal equals false. And if we do this, if we run this, we get all the different indices and outputs as well. So it gives us the configural fit, metric, and scalar fit. So the CFI value for the different models, the RMSEA value. It gives us the lower confidence interval for the RMSEA and the upper confidence interval for the RMSEA. We haven't actually talked about the use of these confidence intervals yet. Let's see, maybe we still get to that. And then we have the SRMR, so we can actually compare how the lack of fit changes as we go into more restricted models. We also have a couple of additional fit indices, gamma. We have the non-centrality index, and then we have the delta. So this is again the difference in CFI from configural to metric, and then from metric to scalar. So what is our change? And as you can see, again, we have the same kind of information here. The same for RMSEA, and then also for the gamma and the centrality index. And as you can see, all of the indicators, so the CFI, the change in CFI here, change in RMSEA, and also in gamma and in the centrality index, all indicate that we have metric invariance. But similar to the other command, if we look at the CFI, we are above the threshold for change for the CFI. We are below the threshold. Actually, if you remember, RMSEA typically rewards simpler models, and our scalar model obviously is simpler because it has fewer parameters, so we actually have a slightly better fit here. But the gamma gives us reasonably good index again, but the centrality index actually is above the threshold again. So overall, looking at a number of additional parameters, again, we come to a similar conclusion that potentially we may not have scalar invariance. It's really like borderline, and we would need to now run the modification indices to again see, are there some parameters that are potentially useful to be freed up across our different groups, or can we potentially just compare correlations because we have very clear evidence that there's metric invariance, right? So this was the last command that you need in your Ninja toolkit to become a measurement invariance warrior. Okay, so that is it. So we have covered the main things. So you have all the little tools, the main tools that you need in order to test measurement invariance. There are a couple of additional bits and pieces that we could talk about, but this is essentially, like the main stuff. So if you go back through your commands, this is all you need to do. Specify your model, constrain your model. So first of all, run separate parameters by group, then constrain it by hand, either with loadings and intercepts, or if you want to do it very simply, you can just run the omnibus test first. Right, so we could say here omnibus or overall test of measurement invariance. Right? So that is basically it. And that's all you need to do in order to become an awesome measurement invariance detective ninja. Remember, save your script.